even if it doesn't work. But it might. It might. A lot of people working really hard on it. I just need to be convinced by somebody that knows what they're talking about that mathematically that's going to be something that makes sense. Okay, what are we talking about? I've not graded your exams yet. So I've almost graded your exams. Almost. By the way, yeah, no, let's go with it later. I was going to ask you about an exam question that I've changed my mind about. Actually, I'll make one. I'm going to make one comment. If you use a property of linear algebra or a theorem, and that theorem requires that the vector space is finite dimensional, and I go out of my way to say as a hypothesis of the statement of the problem that the vector space is finite dimensional, like, for example, the equivalence of injectivity and invertibility deeply depends on the fact that the vector space is invertible. And man, you guys are happy to just write down invertible and injectivity is the same thing without writing down also that the reason that's true is because V is finite dimensional. So as an extra challenge, you want an extra challenge, write me down an injective operator that is not invertible with infinite dimensional vector space. There you go. Just do that. Right? If like I'm gonna maybe I'll even ask you that question in the future at some point. Injective and invertible are not equivalent unless the vector space is finite dimensional, right? At least in the context of this class. So be careful with that. Remember I told you earlier that if I put a hypothesis in a question and you didn't use it anywhere, you should be worried. It's not a major part. I'm not going to give people zeros for not noticing it, right? But man, do not blithely write down injective and invertible mean the same thing without saying that it's because V is finite dimensional, even circling it or something. Yeah?
Didn't we already do that? Or an operator, and it's like one, two, three, and then
you have to show me that that. So I actually put an idea for one on the board. You just have to show me that it's linear, right? And and also I didn't prove that it was injective either. I just asserted it was injective. Okay. So where are we at in this pile of stuff? We were talking about. Oh yeah, we were gonna do upper triangular matrices real quick. I'm not gonna spend a ton of time on upper triangular matrices, but not upper triangular. We did upper triangular, but diagonal matrices. So first thing we're gonna do. This is the topic of 5C, and 5C is about eigenspaces. And diagonal matrices. That actually the error I'm talking about, I'm making a big deal out of it, stick it in your heads. It's going to be like a 1-point subtraction if you did that, right? But I got to stick it in your heads because there's other professors who would yell at me if I didn't make you guys do that. And I have written this way off the side of the board. I'm trying to record this. So let's see. I can write to rate. Okay. So we're going to start with the definition. An eigenspace an operator T, an L of B, corresponding to lambda F is E lambda E, that's the notation for it. I think it's E for eigenspace. And it's the null space. Okay, so another way of thinking about it is E of lambda T is all of the eigenvectors T associated to an eigenvalue lambda. Oh.
Lambda is like kind of kept general on purpose.
I mean, so yeah, if there's nothing here, then lambda, you define it this way so that you can talk about, you can actually use this to investigate when thing is an eigenvector and when it's an eigenvalue, when it's not. If this null space is just the zero vector, then lambda is not an eigenvalue. If there's anything in here at all that's not the zero vector, then lambda is an eigenvalue. Right. So the only time when this is the way Axler sets this definition up, right? Is that Axler sets this up in such a way that it's possible that lambda could not be an eigenvector, an eigenvalue. And you detect that by this null space just being the zero vector. You could set this up with a definition where you start by assuming that lambda is an eigenvalue. But he's trying to build it all into one definition, sort of, so that you get all the eigenvalue stuff like as a bonus.
And does this space have to be one dimensional?
No, that's the big difference. This is going to be all the dimensions. So for example, if P is equal to the identity operator acting on C2, then the eigenvalue corresponding to 1 of T is equal to all of C2. Everything is an eigenvector. Right? Because it's always the case. I mean, so this is supposed to be a 1 here, but it was not supposed to be a projection. It's supposed to be the identity, right? The idea here is that T of V is equal to V for every V. If TV is equal to 1V for every V, then every vector V is an eigenvector for 1. And so all of two-dimensional vectors must be in the eigenspace of the eigenvalue 1. Yep. Yeah. Yeah. Uh-huh.
Is that one? Is that a 1 or
There's a 1. It is a subspace of V.
So it's like a span.
It's a span of a set of eigenvectors. Yeah. It does. Yeah. 0 is in. I mean, it's going to be a subspace, so it's going to also include 0 as part of it, right? So 0 is not an eigenvalue, but to make this, or an eigenvector, to make this a subspace, you have to include it, which is why it's set up as a null space. Since it's defined as a null space, it must be a subspace. 0 is not an eigenvector, but it's like what this contains is 0 and also all of the eigenvectors corresponding to lambda. So 0 is always in here, but 0 can never be an eigenvector. We've made that part of the definition of an eigenvector, that an eigenvector can't be the 0 vector.
It includes the eigenvalues that correspond to
Well, no. Lambda is, if there's going to be anything in here that's not 0, lambda is going to be an eigenvalue, and this space is going to contain all of the eigenvectors. I mean, how do we define what it means to be an eigenvector? When do we have an eigenvalue? That's the first thing. When did we actually define an eigenvalue existing? We said TV was equal to lambda V for some V, right? That's what we meant by lambda being an eigenvalue. And then if lambda is an eigenvalue, that meant that T minus lambda I V was equal to 0, right? This is an equivalent way of writing this. Lambda being an eigenvalue means T minus lambda I V is equal to 0. But then that's the same thing as saying that V is in the null space of T minus lambda I. Now, this is an existence definition that says there exists a vector V that makes this true. So we're extending the idea here to say, let's just find every vector that's in the null space of T minus lambda I. Because if you're in the null space of T minus lambda I, then it's necessary, if V is in the null space of T minus lambda I, then it must be the case that TV is equal to lambda V. So anything in this null space is a vector, an eigenvector for lambda. Except the 0 vector. Except the 0 vector. Okay. Yep.
Does V control the basis?
Oh, that's a good question. Okay. So T doesn't have a. Okay.
For V?
So does V control the basis for T? So where we're going with all of this eventually is to say when it is possible. If you guys remember 206, one of the big theorems in 206 was that you could find a basis of eigenvectors that turn any matrix into a diagonal matrix, right? There's some matrices that could be made diagonal. and you need a basis of eigenvectors to do it. So the answer is yes. There is going to be a thing where we're going to take T. We're going to find a basis of eigenvectors for the space V if there's enough of them. And if we can do that, then we can turn T into a diagonal matrix. We're going to play exactly the same game here. So yes, in some sense, if T is nice, then non-defective is the way of characterizing that. So if T is not defective, then eigenvectors will turn out to be a basis for the space V. Okay. In fact, I think that maybe he's got a more enlightening example here. So he says, okay, so I guess maybe we'll hook this up with the idea of a diagonal matrix first. Okay. So diagonal matrices, but keep this in the back of your mind. We're going to be dealing with, this gives us subspaces of vectors, so subspaces of V. And now we're going to turn to representations of operators that are even more special than upper triangular. So a diagonal matrix has only any non-zero entries. A matrix is diagonal. N by N matrix is diagonal if non-zero entries only appear on the diagonal. So one way of writing that is like this. So there can be non-zero entry. If there are going to be non-zero entries, they must be on this diagonal, and there's zeros everywhere else. Is the zero vector, is the zero matrix diagonal? Sure, right? It's zeros up here and zeros down here, it's diagonal. All right. So here's an example that Axler lays out. So he says, okay, as an example of a diagonal matrix, consider the matrix A is equal to 8, 0, 0, 0, 5, 0, 0, 0, 5. It's matrix A. It's diagonal because it only has non-zero entries on the main diagonal. And he says, define an operator T of V to be equal to AV for V in C3. So T of a vector just multiplies the matrix A times the representation of that vector. Let me make sure I'm copying his language here. Does he actually say that? I mean, you gotta be able to, fine, I'll do it the Axler way. Okay, suppose A is the matrix of T with respect to some basis V1, V2, and V3. So we start with a vector space V. Suppose that this is the matrix for T. So here we're thinking about T is taking V, and the matrix of T is 8, 0, 0, 0, 5, 0, 0, 0, 0. Okay, these are the pieces here. I've got a three-dimensional vector space V. It's got a basis V1, V2, and V3. And suppose the matrix with respect to that basis is 8, 5, 5 on the diagonal. What that means is you can actually read off what T is from the matrix, right? T of some vector V. Remember what T does is it's supposed to expand that into C1, V1 plus C2, V2 plus C3, V3. That's what T does, right? What does T do to the vector V1? Well, multiplies it by 8. And what does T do to the vector V2? Well, this is the V2 column right here, and here's V1, V2, and V3. That means T of V2 is equal to 0 V1 plus 5 V2 plus 0 V3. Remember, you can read off the operator from the matrix, right? Because it tells you exactly what it does to the basis. T takes V1 and it spits out 8 V1s and 0 V2s and 0 V3s. 8 V1s and 0 V2s and 0 V3s. What does T do to V3? 0 V1s and 0 V2s and 8 V3s. Sorry, 5 V3s. Right? That's what the matrix does here. It tells you how T acts on the basis. So what does T do to a general vector V? Well, that means that, in fact, I can think about it this way. T of V is T of C1 V1 plus C2 V2 plus C3 V3, which is C1 T of V1 plus C2 T of V2 plus C3 T of V2. Oh, but I know what that does. This is 8 V1 and 5 V2 and 5 V3. The operator is really simple. T applied to a general vector just takes the basis elements and multiplies the first one by 8 and the second one by 5 and the third one by 3. Very simple operator. Diagonal matrices turn into really simple maps. Trying to remind you about the connection between the matrix of an operator and writing its formula down. So this is the way that you go from the matrix for an operator to what its formula is. Okay. Okay. So what's this? What's the eigenvector of T? What's the eigenspace of T corresponding to 8? Well, let's see. What does T do to V1? 8 V1. What does T do to V2? 5 V2. What does T do to V3? What does that mean about V2 and V3 compared to V1? First off, what can you say? I wrote this equation down. What can you say about like V1, V2, and V3 with respect to T? I mean, can you tell me anything about the numbers 8, 5, and 5? Does any information at all come out of the fact that I have the system of equations written down? What do you see there? Because to me, what I start seeing is TV equals lambda V is what I see when I look at that. I see the eigenvalue equation. So what is this equation telling you? 8 is an eigenvalue, right? 8 is an eigenvalue. Does it have an eigenvector? V1. How about V2 and V3?
Eigenvalues 5.
5 is an eigenvalue. And V2 and V3 are eigenvectors for 5. Are there any others? Well, no, you chopped up the whole space, right? That's it. So what's this? What's the set of all vectors that corresponds to 8 as an eigenvalue? Not V1, the span of V1. Span of V1. Let's think about why that might be true, right? So I'm making a claim here about the way eigenvectors act, right? What I'm saying is that if you have an eigenvector, I'm saying it like an eigenspace is a subspace, is what I'm saying here, right? So is it the case that if I took some multiple of V1 and I apply T to it, what comes out of that? CTV1, and what's that equal to? C8V1, but I could rewrite that productively as 8 times CV1. Notice, T times CV1 is equal to 8 times CV1. So if V1 is an eigenvector, every scalar multiple of V1 is also an eigenvector for the same eigenvalue. And that's why we say span here. What's this?
Correct to say that he is the set of all
Yeah, it's like the subspace containing or like contains. Yeah, it's the span. You have to construct it as a span to make sure you get 0 into things. Yeah, that's why you want to think about it as a span. right, in this case, or a null space if you like to. Okay. So the idea here is that that you can look at an operator with a diagonal matrix, and it's really easy actually. If you have an operator and the matrix is diagonal, it's very easy to write down what the eigenspaces are. Very easy. In fact, your 206 memory should tell you the whole point was you get a diagonal matrix, you could just read what the eigenvalues were. You do all that row reduction, you could just read the eigenvalues. Okay. Okay. I'm gonna write a theorem down. I want you guys to give me a one-line proof. One-line proof. Now, Axler's proof is not one line, but I don't want you to tell me the idea of the proof in one line, which is the following. In fact, I'll even tell you the name of the theorem. In fact, yeah, I'm just gonna tell you the name. I'm not gonna write the theorem down. I'm gonna tell you the name. You tell me how it's proved. Sum of eigenspaces is a direct sum. That's Axler's name for this theorem. I'll write down the actual definition of it in a second, the formal statement of the theorem in a second. What he's saying is, if you take two eigenspaces together and you form all the possible combination of those eigenspaces, it's not just a sum of sets, it's a direct sum of sets. Why should that be true? What needs to be true for a sum of sets to be a direct sum? Their intersection is the zero vector. Why are eigenspaces going to intersect only at the zero vector?
The eigenspace contains all the vectors associated with that underlying eigenvalue.
Okay,
So
it's going the right direction.
there's nothing to do.
Why? No, almost.
Eigenvectors are linearly.
Eigenvectors can't be linearly.
Well-
Well, okay, yes. Okay,
Of different eigenvalues.
yes, there we go. Right, so
Every eigenvector only has one associated eigenvalue.
so that's basically the same like idea here. Yeah, so this has to be drilled into your heads because so many proofs pivot off this point. Eigenvectors associated with different eigenvalues are linearly independent. We proved that in the last section. Eigenvectors associated with different eigenvalues are automatically linearly independent. So this is going to use the fact that if lambda1 and lambda2 are eigenvalues of t, and lambda1 is not equal to lambda2, and tv is equal to lambda1v, and tw is equal to lambda2w, then v, oh man, that's terrible. V and w are independent. So a long way of saying the same thing. Eigenvectors associated with different eigenvalues must be linearly independent.
What does the sum equal?
What do you mean? No, okay. No, that's a big deal though. Sometimes it's equal to V and sometimes it isn't. I'm saying an arbitrary sum of eigenspaces. It's a direct sum. So it seems like a contentless thing, but the idea that I'm saying is if you start with E of lambda1 t and you set sum it to E of lambda2 t, and what I mean here is the collection of all eigenvectors associated with lambda1 and all eigenvectors associated with lambda2 plus the zero vector, that this is the same. That set sum can be written with a direct sum symbol. This is the statement at the core of that theorem.
But
Right.
those are both subspaces.
This is a subspace of V and this is a subspace of V. So all of this live inside of V as a subspace. Now we don't know it's equal to V unless like something really special happens. Yeah, so do you guys actually remember the matrices that were always diagonalizable in 206? So it's a really, we're not going to get to it in this class. It's actually a big part of 406 is this theorem. But there's a family of matrices that this always works for called the symmetric matrices. So a symmetric matrix has the property that if you take the transpose of the matrix, you get the original matrix back again. That's in real numbers. It means that a matrix like 2, 3, 3, 1 is symmetric because if you turn the rows into the columns, you get the same matrix back again, right? In complex numbers, use something called Hermitian matrices. And now this is called the conjugate transpose. you take a matrix and you flip it symmetrically, but you take the complex conjugate of all the entries. So these are called Hermitian. These are called symmetric. And then there's another family of matrices or operators that are called normal. Normal is if this happens. You take one way of thinking about this, you take a matrix and you take the complex conjugate of the representing matrix, that you can switch the order. So this is called normal. And in 206, what you're supposed to prove in 206, or at least be told, that everything that looks like this can always be diagonalized. It's called the spectral period. It's like one of the main, or the diagonalization theorem, I think, in Lei's book, right? It's one of the main results in matrix theory, is it tells you precisely which matrices can be written in diagonal form when you have enough eigenvectors to make a basis for it.
So what are the words written on the side of
Symmetric, Hermitian. I know. Well, there was this mathematician called it like Hermite. And so he gets a matrix named after him.
And then who's the last guy?
It's called normal. There's a contest for you, by the way. What is the word that gets used in mathematics that has got the most different definitions that have nothing to do with each other? And normal is certainly in the ballpark for that sort of thing. I'll leave that to you guys to think about. Here's what the actual theorem says. If V is finite dimensional, and T is an operator on V, and then we'll let lambda 1 through lambda n be distinct eigenvalues T, then E lambda 1 T plus up to E lambda n T is a direct sum. And then we don't quite get the theorem that says it adds up to all of V, but it says we might. The dimension of E lambda 1 to direct sum to E lambda nt is less than or equal to the dimension of V. It could be all of V, but it's going to be pretty special when that happens. And then the proof of this, like I said, the proof of this goes by linear independence of distinct, linear independence. You should read this proof, make sure you understand it. But the basic idea is that you have linear independence of eigenvectors of distinct eigenvalues. That fact is like a central fact in this sort of analysis. Okay. I'm not going to do the whole proof. You read it. You do it, as my 3-year-old would say. Okay. Now the idea is to connect. So like Aria was talking about, like there's a question here about when I have eigenspaces that make up all of V. Okay. And so that we're going to connect up the idea of a matrix, a special kind of matrix representation. And this sum up here actually having a dimension equal to the dimension of V. Enough, and the dimension, direct sum of the E lambda I T is equal to the dimension of V. This is kind of what we're going to do. Don't get intimidated by this symbol right here. I just mean if you do the direct sum of all the eigenspaces, the dimension of that whole thing is equal to the dimension of V. And it turns out to be the case that this happens precisely when you can find a basis that makes this representation diagonal. A basis of eigenvectors, for those of you that are married to the idea of matrix algebra or matrix analysis in Euclidean space. An operator is called diagonalizable. Operator T in L of V is diagonalizable if the operator, I like all these words, if M T G1 up to Vn is diagonal for some basis. We have a symbol for that. That says the matrix of T with respect to V1 through Vn is diagonal for some basis V1 through Vn. I can find some basis so I get a diagonal representation. Yep.
Why is it not if and only if?
Well, this is a definition.
Oh,
Definitions are always if and only if.
so if it says if, I can say if and only if.
In the context of definitions are always logical equivalences. A definition is always logically equivalent. If I say something is diagonalizable, I need it has a diagonal matrix representing it for some basis. If it has a matrix representing it for some basis, I call it diagonalizable. Every definition is an equivalence. Okay, so here is the problem is when are things diagonalizable? That's actually a really hard question. But sometimes we get lucky. So Axel is going to throw a bunch of conditions at you that seem like they may kind of build up to something that looks like a cool theorem, but probably like it's going to be sort of dissatisfying. And then after we do that, I'll give you a theorem that actually gives me one case where I know for sure that a matrix is, or that an operator is diagonalizable. So this is a theorem. The idea here is these are the equivalent conditions for diagonalizability. And if you want a better theorem, you got to take the next course in the sequence. Okay, so suppose C is in LV, or V is finite dimensional. Let lambda 1 to lambda n be distinct eigenvalues of T. Okay, the following are equivalents. Okay, condition 1 is easy. T is diagonalizable. Condition 2, the completely illuminating statement, V has a basis of eigenvectors. Problem is, how do I know when that's true, right? I mean, like, duh, of course, if V has a basis of eigenvectors, I'm probably going to be able to find them as a diagonal matrix, right?
The list of all eigenvectors corresponding to
It's not a list, it's a subspace, right? That's the, and so, and actually, no, highly not. So a basis for an eigenspace. So a basis for an, this basically is going to require that we have bases for eigenspaces. And eigenspaces can have infinite numbers of bases. Bases, there's like no control over the number of total bases. That's why we have to use dimension as the way that we're going to use to build this, because it's the same thing with like in R2. You know, this is a basis for R2. But any scalar multiple of this and any scalar multiple of that are a basis for R2. And also anything, I mean, as long as these two vectors aren't linearly independent, any combination of two vectors is a basis for R2, right? So we're not going to be using dimension. We're not going to be using number of vectors. We're going to be talking about dimension to do this. Yep.
Can you explain what number 2 means again?
I would be happy to. Okay, that means that V has a basis. So I mean, we're going to go through the like how this argument works, and hopefully it'll be more clear there. But the idea here is I have enough linearly independent eigenvectors that they form a basis for the whole space.
And do the eigenvectors has to be like corresponding to certain eigenvalues?
They don't actually. No. There's a special case when I know automatically I have enough eigenvectors. So I'm gonna let the cat out of the bag a little bit, I guess. So the theorem is if you have the same number of distinct eigenvalues as you did the dimension of the space V, then automatically the operator is going to have a basis of eigenvectors. That's like sort of one case where this works, but no, this is harder to achieve than you might think it is to have a basis of eigenvectors. This says that I have to have enough linearly independent eigenvectors that I can build out all of V with it. It doesn't say anything about how they're associated with lambda 1 through lambda n, and that's actually the problem with why this is so hard. Condition 3. There exists. There exists one-dimensional subspaces one up to un of V, each invariant under T, such that V is equal to U1 direct sum U2 direct sum UN. This is not supposed to be an n here. This is supposed to be an m. I apologize. I'm trying to say that this could be strictly less than the dimension of V. So this is my bad. I thought it was. I wrote this down in here. There could be fewer eigenvalues than there are subspaces. The point here is that you should think the dimension of V is equal to n. Condition 4. V is equal to E lambda 1 T direct sum E lambda 2 T direct sum lambda M T. Notice there's fewer of these potentially than there are of these. This is attached to the dimension of the subspace. This is attached to the number of eigenvalues that there are. So the point is these don't have to be one-dimensional. Eigenspaces could be lots of dimensional. And then finally, condition 5, the dimension of V is equal to the dimension of lambda 1 T. The dimension of V. So there's a lot of ways of measuring when a matrix or when an operator is diagonalizable. It just turns out to be the case that frequently we don't know any of these are true. Yeah, because if you have 4, each one dimensional subspace, this is part of the proof is that one-dimensional subspaces correspond to scalar multiplication. That scalar is an eigenvalue, and so you can assemble these into the eigenspaces. If this is true, you can just assemble these into these. Okay, so again, let's go through this again, right? Remember, T diagonalizable means that it has there's a basis so that it has a diagonal matrix attached to it. V having an eigenbasis of V having a basis of eigenvectors means that there's enough linearly independent eigenvectors of T so that I can build out all of V. Now we've got an invariant subspace characterization where these are one-dimensional. Earlier we showed that one-dimensional invariant subspaces are just spanned by single vectors, and so they're like scalar multiplication. Each one of these corresponds to an eigenvalue, not necessarily distinct. This is saying that the eigenspaces are enough to build up all of V, which is pretty clear to see that this one and this one are the same, because I could build out a basis for this, and a basis for this, and a basis for this, and a basis for that, and then glue it all together to a basis for all of V. And then finally, just a dimension count. Do I have enough vectors in the basis itself? And without even finding the vectors, can I just write down the number of vectors that there are? Okay, So let me show you a way that this works and a way it goes wrong. I have space to do that. So I can talk to this example. So this guy, if I have like 1, 0, 0, 2, say. How do we even say that? Let's do this. T of VW is equal to V2W. Okay, so this thing has eigenvalues. Lambda is equal to, lambda 1 is equal to 1 because T of V0 is equal to V0, which is 1 times V0. So it has, T of V0 basically spits the same vector out. So it has an eigenvalue of 1, right? It didn't do anything to the vector, so it left it alone as eigenvalue of 1. Also, lambda 2 is equal to 2 as an eigenvalue because T of 0W is equal to 0, 2W, which is 2 times 0W. So this is an eigenvector because T took it and multiplied it by 2. In this case, we know that we could find a basis that T has got a diagonal representation because, well, we can just do a dimension count. What's the dimension of the space that we're acting on here? This is two-dimensional space, right? T can be thought of as taking F2 to F2. What is the dimension of F2? Well, it's 2. What's the dimension of the eigenspace associated with the eigenvector 1 of T? Well, there's one vector here. The dimension of this is 1. It's spanned by the vector V0. The dimension of E2T is also 1. Now, from this statement right here, can you tell me if T has a diagonal matrix or not? Can I find a basis for F2 so that T has a diagonal representation? Well, yeah. This basically by 5, the dimension of the eigenspaces adds up to 2, and the dimension of the space is 2, and that means 5 implies 1, right? I have enough linearly independent eigenvectors that force the dimension count to work. So since the dimension of the eigenspaces adds up to the dimension of the whole space, I could find a basis. In fact, if you do this, you'll find that T of VW can be represented with with respect to V1 is equal to 1, 0, and V2 is equal to 0, 1. The matrix of T is 1, 0, 0, 2. You can find a basis that gives you the diagonal matrix. How about a defective case? So this matrix, we'll do T of VW is equal to V plus W, W. So that operation turns out to have one eigenvalue. I'm not going to prove it. I'm just going to do it. I'm going to assert this to you. This operator has lambda equals 1 as its only eigenvalue. And that by itself is not enough to keep it from being diagonalizable. But if you actually analyze this and figure out its eigenvector, it turns out the only eigenvector is the eigenvector, one of the eigenvectors here is E of 1t is the span of the vector 1, 1. That's it. There's nothing else. There's no more eigenvalues to use and no more eigenvectors to use. So this operation has one eigenvalue, but only one linearly independent eigenvector. Doesn't this make sense? V plus W, W? Oh, it's supposed to be 0, 1, 0, 1. Is it 1, 0? Don't do it off the matrix. Okay, so is this diagonalizable? And the answer is no, right? It's not diagonalizable because there's not enough eigen stuff here. Somehow there's something defective about this operator where there's not enough stuff this is holding, that this is acting like matrix multiplication on. There's one eigenvalue, but there's also only one eigenvector. And one eigenvector, the span of one eigenspace, this dimension being one, is not enough to span all of a two-dimensional space V. Okay. In 206, you would have learned this. You would have learned that 1101 is a defective matrix. And the language that would have got used there is the algebraic multiplicity of the eigenvalue doesn't equal the geometric multiplicity of the eigenvalue. And there's not enough eigenvectors. You'd expect it to be the case that this should have a two-dimensional eigenspace, but it doesn't. And that's why they call it defective. Okay. Now, we can't use any of that language because we're not going to get the characteristic polynomial until like chapter 8 or 9 of this book. So we can't use the idea of algebraic degree. And that's why this is hard to do. It's hard to look at this operator and say, this one is going to be diagonalizable and this one isn't. Okay, so it's a major problem when you're in algebra to distinguish between cases that look like this and cases that look like this. So what we'll do next time is we will walk through the basic idea of some of that proof. I really want you guys to read this argument, not because there's anything profound about any of the individual steps, but because each step here is because there's 5 pieces and all of these equivalences, each step involves math that connects up a bunch of stuff that we've already talked about. So read this argument. We'll go through it next time, at least a sketch of these lines here. And then we'll move on to talking about, we're starting our product spaces, which is like maybe the most beautiful area of linear algebra. So, yep.
And you said M is less than or equal to N?
Yeah. Yeah, you can't have more. We proved you can't have more eigenvalues than you have dimension in the space you're living in. We did show that, right? So there can't be more eigenvalues than you have the dimension of the space. That can't happen.
Does each eigenspace have its own basis of
Yes.
eigenvectors? Okay.
But they're not unique though.
Okay.
Each eigenspace has a basis. I mean, it's a subspace, so it has a basis. And so essentially what we're saying is T will be diagonalizable if I take this basis and this basis and this basis and this basis and glue it together, and I get a basis for all of these.
Okay, so V has a basis of eigenvectors. Those are all made up of that basis is made up of individual
These
bases.
guys. Yeah.
Okay.
So this is basically saying, so when you do this, when you say this line, you're saying, okay, don't pay attention to the eigenvalues. If you just know you've got enough eigenvectors, you know it's enough to be diagonalizable. This says, if you know you have enough eigenvalues with invariant subspace, then you've got enough of these. Okay, each one of these comes with one of these.
So there's like a case where it's like if you know the eigenvalues, then you know this, and if you know
Yeah.
eigenvectors, you know. Okay.
Yeah. And the special case is if you have, say you're working at a 10-dimensional space, if you have an operator that has 10 distinct eigenvalues, then all the eigenvalues have to be linearly independent, which means that must hold, which means it must be diagonalizable, right? So if you have enough different eigenvalues, you automatically get to be diagonalizable.
Okay.
The problem is in like cases like this, where there's only one of them, and it's possible that even though this should really be dimension 2, it's only dimension 1.
Okay, so this say that because like lambda, why is that?
I didn't actually prove this. I just stated it. I didn't prove this. I mean, the reason this holds is because if you do, if you take yourself, yeah, I'll write it. If you write down T of VW is equal to V plus WW, right?
Yeah.
And on the other hand, you demand that that's equal to C times VW. This is how you actually find an eigenvalue, right? Okay, so let's actually do that. So CV CW must be equal to V plus W W. Okay, but that means CW must be W. So C must be 1.
Yeah.
But now 1V is supposed to be equal to V plus W. So how could that possibly be true? Well, it can't be, because in order for this to be an eigenvalue, like suppose V isn't, we know that there's going to be a 0, like suppose W is not 0.
Okay.
I already know that like this expression right here means that W can't be, like they can't both be 0.
Okay. So
Let's say suppose W was 0. What would that mean? If W was 0, I mean that V was equal to, so would that be, so that would make this equation true, right? If V was equal to 0, I'm sorry, if W was equal to 0. What if V was equal to 0?
then W.
And is 0, 0 an eigenvector? No, it can't be. 0 can't be an eigenvector, right? So that means the only way for this equation to be true is if W is equal to 0 and V is equal to 1. Or not B is equal to 1, but like That's it, just that
But the
W zero.
W is zero, and then that makes.
And then, yeah, then that means that basically, you know, the TV of zero is equal to V zero.
Yes.
And that's what makes you the span of
And
one.
then, okay, and then that's, okay.
Yeah, so I didn't prove it, I didn't have time to prove
No,
it.
yeah, okay, that one, thank you.